So next we're going to do another problem. Let's see how this one works out. Blood flows in a horizontal artery of diameter 3 times 10 to the minus 3 meters. At a smooth constriction, the blood pressure drops by 40 Pascal. The flow rate is 1 times 10 to the minus 6 meters cubed per second. The density of the blood is 1.05 times 10 to the 3 kilograms meters cubed. What is the diameter in the constriction? What is the diameter of the constriction? So they want to know the diameter. They want to know the diameter here. Let's call it D2. They've given us D1. They've given us the initial flow rate, or the flow rate everywhere, is 1 times 10 to the minus 6 meters cubed per second. Okay? And once they give us the flow rate, we know that that's equal to area 1, velocity 1, which is equal to area 2, velocity 2, which is going to be equal to pi, let's call it radius 1 squared times velocity 1, which is going to be equal to pi radius 2 squared velocity 2. So with this, we can use this volume flow rate to figure out what the velocity, the initial velocity is. Okay, so I'm going to write this down over here. Velocity 1 is going to be equal to 1 times 10 to the minus 6 divided by pi 1.5 times 10 to the minus 3 squared. Okay, and we'll plug that into a calculator and we'll get a number. So once we have velocity 1, we know radius 1. We still don't know, what's that? Okay, we still don't know this and that. We don't know the velocity 2, and we don't know radius 2. They want us diameter, so they want us to figure this one out. How are we going to figure out the final velocity? Well, we've got two equations, two unknowns. We have only one equation. And in math, you know that if you have two unknowns, you need two equations. So the other equation is going to be Bernoulli's equation. Let's write this down. Pressure 1 plus rho g y1 plus 1/2 rho v1 squared is equal to pressure 2 plus rho g y2 plus 1/2 rho v2 squared. And they didn't give us the pressures, but they told us that pressure 2 is equal to pressure 1 minus 40. So we can plug those in. P1, oh wait a minute, before we do, this is a nice example of Bernoulli's equation where it's not going uphill, it's not going downhill. Okay, you measure the heights from the center of the circular channel, right? And there's no difference in height. So y1 is equal to y2. Okay, both these two terms cancel out. So as usual, you have 6 terms in the Bernoulli equation. It quickly drops to 4. Good. Now then there's the pressure, and we can write this down. Plus 1/2 rho v1 squared is equal to pressure 1 minus 40 plus 1/2 rho v2 squared. So now we can cancel the pressures. And so then Bernoulli's equation simplifies, and we can figure out, let's see, we can say 1/2 rho v2 squared is equal to 1/2 rho v1 squared plus 40. Okay, great. So these, at this point we could stop and we can say that these are two equations that we're going to use. Okay, we're going to have to pull out our calculator and we're going to put in the value of our V1. Once we know V1, we can figure out what velocity 2 is. Once we know velocity 2, we can plug it in to over here, okay? And I'm going to rewrite this. This was equal to 1 times 10 to the minus 6 meters cubed per second. So once we figure out velocity 2, we can plug that into this equation and figure out what radius 2 is, and then what diameter 2. So this is how working on a problem really looks like. Okay, if you look at a done out example in a book, it can be intimidating because it's so brief and so short, because people like to try to save space in text. So like this, okay? So this is the done out answer. So Bernoulli's equation, you cancel the two potential energy terms, right? The height terms, because it's not going uphill, it's not going downhill. Then the flow rate was given, area 1 V1, pi r squared V1. So we solved for V1, okay, 0.14 meters per second. If I want, I can go back. Yeah, I'll do it. 0.14 meter per second. Okay, now we go back. So then we make the observation that pressure 2 is 40 lower than pressure 1. So that allows us to cancel the P1s. Okay, and that P2 just becomes a minus 40. What they're saying here is that's leaving us only V2 as an unknown. Okay, once we figure out V2, okay, 0.31 meters per second. Wait a minute, so V1 is 0.14, V2 is faster, right? It's 0.3. Does that make sense? Yes, because it's a constriction. It's not going uphill, it's not going downhill. It's just going across. And as it's getting narrower, okay, continuity says, okay, that's nothing to do with uphill or downhill. Continuity says as it's going, it gets narrower, okay, because the volume flow rate is the same, it's got to be faster. Yes, we didn't make a mistake. Good. Then we go back to our continuity equation again, and we're going to say the flow rate that they gave us is equal to area 2, velocity 2, pi r squared V2. We know Q, we know V2, we're going to get R2. R2 is equal to, works out to be 1 millimeter. Okay, great. The diameter, we double it, 2 millimeters. That's how you do this problem. It's a lot of turning the crank, but it's actually not tricky. Okay, there are tricky problems, and especially in the mechanics and rotational motion stuff that you had to do. But this stuff here, in my opinion, isn't tricky. Okay, it's just two equations to a known, and remembering which your two equations are. It's the continuity and the Bernoulli. Okay.